To IISE transaction webinar series. My name is Yu Ding. I'm the editor-in-chief of IISE transaction, and I'm on faculty of Texas A&M University. IISE transaction webinar series in the fall 2022 features 7 talks based on the articles to be published in the special issue in the journal. The special issue is going to be published as the first issue of 2023. Today is our third webinar in the series, and we are very fortunate to have my colleague and Dr. Satish Bukkapatnam, Rockwell International Professor of Industrial and Systems Engineering with us. Dr. Bukkapatnam received his PhD in 1997 from Penn State. I was actually on the same campus as a graduate student when Dr. Bukkapatnam was there. But I'm in a different department, so we didn't really know each other at that time. And I got to know Dr. Bukkapatnam after I joined the faculty of Texas A&M. Dr. Bukkapatnam was on faculty of USC and Oklahoma State prior to joining TMU in 2014. He's now the director of TIISE Institute of Manufacturing Systems. His research interests are in the broadly defined smart manufacturing area. Dr. Bukkapatnam is a fellow of IISE and SME, associate member of CIRP, and was a Fulbright Tocqueville Distinguished Chair. Today, Dr. Bukkapatnam will speak to us about this very exciting topic of autonomous manufacturing. So Satish, the platform is yours.
Again, thank you so much, Yu. Thanks for inviting me to present, and as well as for the kind introduction. Hello, everyone. It's wonderful to have you all in this talk. And this talk, as you can see, is titled Autonomous Materials Discovery and Manufacturing. And it will be more of perspectives rather than a review in this presentation. And as Professor Ding mentioned, the details of the review are presented in a paper that's been accepted and is set to be published in the IISE Transactions Journal. And before I begin, I have a few rather confessions to make. The most important thing is this field of autonomous materials discovery and manufacturing is one of the strongly interdisciplinary fields. And much of what the paper presented is based essentially on what I had learned from the discussions with my colleagues, some of whom you see in this picture here. And these colleagues include experts in both the experimental as well as the computational aspects of material science and various components of statistical as well as other aspects of machine learning, statistical informatics, as well as control theoretic aspects. And it turns out manufacturing is almost like a man in the middle when it comes to integrating these various disciplines together for AMDM or autonomous materials as discovery and manufacturing. And I hope that my experiences in manufacturing and data science, and of course, industrial engineering in general, can provide some very interesting perspective as well as take on this very exciting field. And therefore, this talk, as I mentioned, will focus more on presenting some of the perspectives that essentially I garnered from discussing these topics with my colleagues on this exciting emerging topic. And some of my perspectives, if they seem a little bit too audacious, we can definitely discuss this further in the question and answer session. And also, this talk is intended to serve as an introduction of sorts to this emerging field. And I hope that this can present some new ideas, opportunities, and pathways for especially the emerging researchers as well as practitioners in this field. And especially those of us in the ISCN community. And this is basically the outline for this talk. The first 20 minutes would be mostly introduction and background to this emerging area. And considering the interdisciplinary nature of this field, I believe that such an introduction and background may be helpful. And thereafter, I will touch upon the two important aspects of what can be termed as an AMDM, or Autonomous Materials Discovery and Manufacturing System. And the remaining time would be for the summary as well as question and answers. To set the stage here, if you look at the recent innovations in materials and processes, they've opened some very exciting possibilities to create an entirely new, radically new kind of products. One example here is the fact that the new classes of shape memory alloy materials, especially the high temperature and extreme environment shape memory alloys, or SMAs. The discovery of these materials are leading to the creation of so-called the morphing chevron wings, as well as other extreme environment structures. Similarly, the discovery of newer kinds of concrete are revolutionizing, are starting to revolutionize 3D printing of whole homes, as well as several consumer products. And these discoveries are essentially fueled by three major global imperatives. The first one is because of the growth in the competitive landscape. There is a need to enhance the performance envelope of various products and systems for the industry as well as the strategic sector. The second is the global push towards green energy as well as green manufacturing is forcing the reduction of the material usage as well as optimal usage of materials and processes and energy. The third driving force is the growing problem of critical material shortage, especially for some of the highly strategic applications, as well as the emerging sectors of autonomous transportation, where battery is going to be critical, and newer hydrogen economy, hypersonics, and microelectronics. While this discovery is an exciting and emerging topic, the process of discovery has traditionally been usually a very long drawn process. To underscore this, let me provide a case study based on what one of my colleagues, Professor Ibrahim Karaman from Material Science, has experienced. He developed an SMA torque tube, basically shape memory alloy component, that became part of the aerospace structures in recent years. But the discovery of this material essentially involved a painstaking effort where he created a precise composition of nickel titanium hafnium system, and it processed through multi-stage processing or manufacturing process, each controlled with a precise set of process conditions to be able to realize the desired shape memory effect that was helpful for functional application. And this process of arriving at this the material composition as well as the processing recipe took about 15 years. And this 15 years essentially involved running multiple iterations of experiments to make sure the end goal of the desired shape memory characteristic is reached by playing as well as tailoring the structure of the material at multiple scales and from multiple ways, looking at the crystallographic, the grains, precipitations, and so on. And if you look into the entire process of innovating this material, it essentially involved a series of iterative experiments. Initial iterations essentially were mostly not successful. And over time, through experimental iterations, they were able to make progress, leading to the creation of the final product system. And this is what took those 15 years, essentially. Make, try, and measure, and then try to make again. This process of iterative experimentation, if you abstract up, is essentially can be seen as having each experiment to be a point in the abstract material design space. In other words, if you think about the entire process of choosing the right experimental point, it essentially boils down to choosing a particular value for the composition, the various process settings, the temperature, the pressure, the force profiles, and so on, so that you realize a particular combination of these properties like crystal structure, grain refinement, etc. And the overall process of experimental iterations leading to the discovery boils down to basically searching this material design space to find the desired combination of the composition as well as the processing conditions to achieve the desired structure. As you can quickly see, such a process of materials discovery, this traditional process, is lengthy and of course can be very expensive. And clearly, with the modern capabilities that we have, we can even think about an audacious goal of reducing this overall time for discovery significantly. And the goal of AMDM, or the Autonomous Materials Discovery and Manufacturing, is essentially to achieve this compression in time and increasing the efficiency as well as effectiveness of this discovery and manufacturing process. So to state the objective, so the objective is essentially to discover novel materials with the specified tailored properties, as well as their manufacturing recipes, automatically and autonomously through the computers by the use of advances in artificial intelligence and data science. And although this goal looks a bit audacious, such AMDM systems have already been in realizations in other fields, especially in the drug discovery type of areas, as well as chemical processes. There have been some recent successes. In fact, a couple of years ago, a paper from Nature talked about a mobile robot chemist that basically goes through the entire lab, scans through the lab, and then goes to the right instrument or the platform to conduct the desired test. And then once the desired test is done, it basically goes and measures. And based on what it gleans from the measurement, it decides where to go for the next round of experiments. And this is a video, and let me know if you're having trouble listening to the audio. I will make some suitable adjustment.
This robot helper has been designed by chemists at the University of Liverpool to help them in their research into developing photocatalysts, which are materials that help produce hydrogen from water using light.
So these are essentially photocatalysts. They are trying to find the composition of the chemical to achieve the desired efficiency in generating hydrogen. And as you can see, this is just a chemical process. And many of these steps are basically take a few seconds. And many of these experimental steps can be done on an experimental bench. But if you try to translate this drug as well as chemical discovery to manufacturing, it might actually have a slightly different connotation. If you think about the difficulties in translating this to manufacturing, one way one can think of is what it actually takes to change the goal into a particular product design and manufacturing recipe. And over the years, the manufacturing community have come up with some kind of a design process. And if you think about what it takes to translate the goal into a process plan, today's process plans invariably talk about converting the specifications into realizing a particular motion path plan for the machine to achieve a desired geometry. So in other words, you can control or generate the geometry based on the requirements. And some of these systems at the high precision level can also control the desired morphology or texture on the surface. But very few of these systems can take the specifications and generate the desired microstructure, material compositions, and so on. And this remains a major challenge, which is how to convert the requirement from the customer so that you are not only able to generate the desired shape, optimized for the morphology, but also for the microstructure and compositions. Why is this a major challenge? Compared to many other systems, most of the materials that we typically use for manufacturing, their processing recipe and how it relates to the desired structure, microstructure, as well as the properties that emerge out of the structure, that relationship remains extremely complex. This relationship capturing the process to the structure of the product that you generate, to the desired, the resulting property and functionality that will be endowed into the project, into the product, that remains a highly complex. And this relationship map is called the PSP map, process, structure, and property map. And to kind of understand this a little bit in depth, if you think about a process, it could include what composition you use, what type of process chain we use, and what type of process settings and its variation you use to create that particular product. And while doing so, if you set these, what kind of product that you get from a geometry, morphology, microstructure, and composition standpoint over multiple scales. And given this type of a product, what would be the performance that would be endowed into this? That remains unknown for most material systems as well as for more geometries. So in effect, if you are trying to build an autonomous discovery system, you should endow the computer with the ability to learn and adapt its processing on the fly, just like what the robot tried to do. And the second aspect when it comes to this challenge is, if you look at what people know today, the material science has evolved to the point where the structure to property mapping is quite mature. There are quite a few computational models that build the relationship between the structure to the property extending over multiple scales, all the way from atomistic or quantum scales, all the way to so-called the continuum scales. But where the limitation lies is in understanding the relationship between the process to the resulting structure. And deriving this understanding is quite complex, and simple set of experiments can be extremely inefficient, because if you try to run the experiments within a particular set of parameters, you are pretty much exploiting. You might end up with highly suboptimal results. But at the same time, if you keep on exploring boldly at random, then once again, you are pretty much exhausting an extremely large space. And as a result, you may not be able to find what would be a useful recipe that you can use. So there has to be a good balance between exploitation, that is trying to locally optimize, versus exploration, trying to try out many different combinations. And also from a manufacturing standpoint, creating bulk scale products that ensures a structure uniformly still remains a challenge. When you look at the structure, I'm looking at geometry, composition, morphology, and microstructure. Controlling this, controlling all of them, even in a part of a few millimeters in dimensions, still remains a challenge. Once you realize, of course, you can determine its property, but realizing that and making this connect between the process and the structure, for the most part, remains a challenge. And also, from a machine tool hardware implementation standpoint, so-called closing the loop poses some interesting avenues for further exploration. If you look at most of the machine tool controls, they are control of the process chain or the equipment motion and settings. Controlling the process state, again, remains an open area, and a lot of work in-process sensing and control are ongoing, and they are all can be made to focus to address this emerging challenge. So this essentially is the overall landscape of this AMDM. Now let's try to look at what such an AMDM system would look like. If you think about an AMDM system, at the outset is essentially a software brain as well as a hardware body. And you can think about this as a cyber physical system. And this software brain is essentially a put together of various advanced data science and AI technologies that include active learning methods, multi-fidelity data fusion to combine this information to enable this active learning, and adaptive control of the workflow, the processing, process combinations, as well as process settings on the go, so that you can actually trace through and iterate those experiments. And the hardware body essentially consists of three components. Essentially, it includes the synthesis chamber where you are making the material and the product, the material handling system that takes that particular material across the process chain, as well as the characterization modules that basically takes the material and runs it through various different tests to assess how well it performs. And this integration of these two systems and the interplay between the brain and the body of this AMDM system poses some very interesting challenges and at the same time the opportunity. And in this context, I'm going to emphasize the idea of autonomy. Of course, many of us have heard about autonomy in various different contexts. But autonomy in itself essentially means it should have two essential attributes. The first is the ability to learn. That is, it needs to sense the environment and create a mental model of the underlying relationships, here the process, structure, and property map based on this new data. And the second is adaptation, which is it should be able to change the way it has been operating or the set of path it's going to take based on the mental model and its updates. So every autonomous system should essentially have this both learning as well as adaptive control of its motion plan in some sense. In addition to this, there are advanced level of autonomy that you can endow your system with. The ability to recognize things, ability to empathize with things, and also make some higher order reasoning about what it's able to perceive. And all of these go into developing an autonomous system. And also in this context, learning requires a specific discussion in the context of manufacturing. If you look at most of the learning systems, they are predominantly based on supervised learning. To make the comparison with autonomous vehicles. These autonomous vehicles work to autonomously recognize the stop signs as well as speed signs to make appropriate adjustments because they were trained with millions of photographs a priori. Using supervised learning methods or deep learning methods, they were able to recognize those signs to make appropriate adjustments. And these systems are used as part of the modern cars. But such type of photographs are very inexpensive to gather. You can just run a car and then make it take photographs on the go and then get those photographs as inputs to train. But in manufacturing, each photograph is one experiment. And manufacturing experiments are almost always expensive. Typically, in an industrial setting, a manufacturing experiment, a single experiment can cost sometimes a few thousands of dollars. So you cannot think about creating millions of such experiments. So we therefore need to think about a clever way to choose these expensive experiments so that you can still be able to learn the underlying PSP relationships. And the ability to choose how to search this high dimensional and complex material design space to learn this PSP relationship is essentially at the crux of active learning, and computers will be used to develop these active learning schemes of an AMDM system. And essentially what the system essentially consists of is to use the data from the experiments, essentially from the characterization as well as in-process sensors, so that this active learning engine or the brain of your AMDM system can learn the underlying relationship and provide input on how to run the next experiment, so that you are getting closer and closer to understanding the underlying relationship, at the same time reaching your desired goal. And this process of active learning doesn't require as many number of experimental points, therefore the number of iterations and hence the entire time to search, to discover can be significantly reduced. And that will help us explore new regions and thereby make this entire search process more efficient. And if we are lucky, we can even achieve optimality or even super optimality. We can speculate on many of these things. So this is essential background about this, the architecting of this AMDM system. And what goes into this AMDM system are the two components, the brain and the body. In the remainder of this talk, I will try to elaborate on both the brain as well as the body. First, about the brain. The brain essentially consists of two components, the forward mapping as well as inverse mapping. The forward mapping basically takes the data from your experiments and develops this PSP map going from process, structure to the property, so that you can predict the property from knowing the various aspects about the process that you are using to create that material or the product. And to do this, these experimental data gets typically fed into some of these computational models, surrogate models, lumped mass models, and so on, to create a typically a statistical representation of the underlying relationship. And the inverse mapping essentially uses these models to develop an efficient and a clever way to search this material design space, so that once we give the goal of what we want to achieve, it basically goes through the process of inverting your models so that it suggests where to run the next round of experiments. The next few slides, I will talk about the forward modeling. The forward modeling, in effect, can be thought of as forward models to capture the relationship between the structure to property, and the second part consists of models to relate the process to structure. If you look at the structure to property models, they could be of two types: computational models or statistical surrogate models. Before getting into the details of those, computational models tend to be basically the derivative of the first principle physics and then mechanisms. And they typically tend to be highly computationally expensive. Therefore, they're used to capture things over short times and short spaces to study the effect of a particular structure on a specified functionality. On the other hand, the statistical surrogate models essentially capture the cause-effect relationships typically gleaned from the experiments as well as from the computational models. And the greatest advantage to using these statistical surrogate models is basically the simplicity, speed, as well as the ability to fuse multiple models. At the same time, be able to help with driving the various inverse models or inverse mapping approaches we discussed earlier. Next comes the process to structure. The process to structure relationship models right now are not fully developed even for most traditional of manufacturing processes. Currently, there are quite a few computational models, statistical surrogate models, as well as some dynamic models available to capture those. So in this presentation, I will try to outline some of those and share some perspectives on both the S to P as well as P to S mapping models. The structure to process computational models, as mentioned, come in various different flavors, depending on at what scale you want to study that particular structure to process relationship. For example, if you're looking at studying the elastic properties or mechanical properties, you look at continuum models like FEM models. And if you're looking at the quantum chemistry in terms of how the hydrogen gets embedded onto graphene, you'd study the quantum chemistry or at best molecular dynamic models. And right now, there are quite a few implementations of these computational models available for the manufacturing as well as the engineering community to use. But it should be noted that each of these models are application specific. And at the same time, they are invariably involve high computational load. Typically, you use some high-end, high-performance computing environment to run many of these codes. And from a limitation standpoint, they tend to assume determinism in the sense that they cannot give you uncertainty quantification. So a lot of hits and misses happen because of this. And most of these computational models, if not all, require some form or the other of calibration. And third and most important component is every one of these models involve little bit of empiricism. And for example, in molecular dynamic models, they use potential functions. And in other cases, they use certain types of correlation functionals. If we don't get them right, the results can be completely almost absurd or aphysical. So this is the thing to watch out for while using computational models. And there are quite a few opportunities to look into each of these aspects and try to develop or further improve these models. And when it comes to surrogate models, there has been lately extreme interest in the material science community in using machine learning approaches as a substitute for some of these computational models, because the surrogate models can be much faster and they can capture this uncertainty much better than what computational simulation models could. And these surrogate models come in one of the following three types. The first type of surrogate models essentially are small components that you incorporate within the computational models to speed them up. You are not creating a surrogate model independent of the computational model, but you take a bottleneck component of a computational model and then replace that with a surrogate model. And the second component, as you can see, is you're trying to create a physics-informed twin. I don't like that word, but I think that communicates the idea here. You're trying to create a statistical model that tries to emulate the relationship that the entire computational model suite captures. Only thing is, it's much faster to execute. And the third type of statistical models essentially fuse multiple computational models as well as experiments to create features for further control and such applications, or they themselves can create other kinds of twins based on such data fusion as well as model fusion approaches. These statistical surrogate models, once again, have certain advantages and limitations. One of the things is they are only as good as the experimental observations as well as the computational models. For newer processes, especially if you go into manufacturing, it is the domain expertise that actually matters quite a bit. So integrating the experiments with computational models and human expertise is something that's being studied actively. And second thing is many of these surrogate models are predominantly capturing the static relationship between your input structure as well as the output property. So they may not be efficient in capturing the time-dependent behaviors that you want to predict. For example, the shape memory effect in many of these systems. So there are some studies that people are looking into in this aspect. When it comes to process to structure computational models, they essentially are focused on taking the process parameters as inputs and developing various kinds of computational or mechanistic models to predict the geometry, morphology, or microstructure. For example, there have been quite a few models in machining that takes the machining conditions and predict the actual geometry and even surface finish. And recently there have been work even within the IE community in looking at predicting the microstructure of 3D printed components by knowing the temperature settings as well as other process conditions in additive manufacturing processes. And there have also been some studies in looking at the microstructure from knowing the actual processing conditions. So if you think about the kinds of models that are of computational kind available to us, depending on the length scale, you get different kinds of models that you may want to apply. For example, if you're only looking at modeling the temperature distribution while you're 3D printing a component, or looking at the temperature distribution in a weld pool or near the edge while you're cutting a metal at the interface between the tool and the workpiece, you typically use what we call as a continuum scale models. And as you try to go one scale down while predicting the microstructure, the dendritic formations, as well as maybe even the atomistic scale phenomena, you basically have to use different sets of models, including phase field modeling, kinetic Monte Carlo, cellular automata, and so on, as well as some first principles models to be able to derive this relationship between the process and the structure. Here, you're pretty much asking the question of if I run this particular material through a particular processing trajectory of thermal history or force fields and so on, how does my material structure result from this entire processing chain that I make the material go through? And such computational models are being developed across different groups. And like any other computational models, they tend to be requiring high performance computing. And as of today, many, if not all, these models have trouble capturing the sharp gradients, thermal as well as force gradients inherent to manufacturing. Let me talk about two specific examples. In 3D printing, the thermals, the temperature gradients can be of the order of 10 power 5. And similarly, in machining, you are actually looking at the singularity where the material actually separates out from each other. These two phenomena are pretty hard to capture using many different models. Also, the processes tend to be transient, and there will be a lot of heterogeneities inherent into both the space as well as in time that needs to be captured. And as I mentioned, the static models have been used as possible substitutes or the fast equivalents of these computational models. But for process to structure relationship capturing, they tend to be quite inadequate because the dynamic phenomena that I just laid out, the sharp gradients, the transients and heterogeneities, they are hard to capture using simple statistical models. One way to addressing this is the use of lumped mass analytical models. So the underlying notion is to borrow the principles of small active degrees of freedom as well as recurrence inherent to many of these manufacturing processes as well as other dynamic systems. And these ideas become the root of developing low-dimensional representations so that you can quickly predict some of the spatiotemporal evolution of the structure due to the effect of the process. And the advantage to using some of these first principles lumped mass models is that you can actually build these models with limited data. And an example here is trying to model the deposition of a material from one of the most common 3D printing process, or FDM, using a 2 degree of freedom analytic model. So the entire idea of how the material comes out of this nozzle, as well as how the material gets deposited onto the surface, can be modeled using a back pressure, or that's the force that the material experiences due to the effect of deposition, as well as the response of the structure to this force in a dynamic fashion. And these reduced order models have been used in various different manufacturing processes by Professor Rao, Professor Kong, and others in this field. And these models can be useful in predicting some of the outcomes, such as the overflow and its effect on the surface, the endpoints in polishing, and so on. And the advantage to some of these lumped mass models is they can be much more interpretable compared to the deep learning models. However, with the availability of more and more high resolution sensor data, it makes it possible to develop recurrent network, deep recurrent network type models that can replace some of these explicit lumped mass system models, and they can be something for our community to pursue in the future. Next, let me spend some time talking about the inverse mapping. The inverse mapping essentially focuses on trying to use these models, the computational models, both P to S and S to P, to be able to determine where to run the experimental iterations. And when it comes to this inverse mapping, historically there have been, we can think about this as two schools of thoughts on sequential experimentation. The first one evolved from the statistical foundations laid by Fisher, Box, and Professor Jeffu and others. And the second one from the decision and control theory developed by Dr. Wald. And if you can think about it, these statistical foundations have evolved into a Bayesian optimization framework. And this is what is typically used in the modern inverse mapping applications. And it basically consists of the ideas of acquisition functions as well as the search strategy, which I will talk about in a minute. The second line of thought led to the multi-armed bandit problems that uses the control theoretic, control model, and control synthesis equivalents, and that have evolved into the ideas of reinforcement learning. And when we think about this emerging Bayesian framework, it essentially uses the initial surrogate model and determines certain acquisition functions, more like an objective function, as well as a search strategy that takes how we can use the outcome of the acquisition function to determine your next experimental point. So when an initial model is fed, the acquisition function is computed, and then based on the acquisition strategy, you determine the experimental point, run the experiments. From the data from the experiments, you update the model, and once again, determine the best X, and so on. You go through the sequence. And how do you design your acquisition function? Essentially is an interesting challenge in itself. It's basically is called the exploration versus exploitation dilemma. It's whether to improve my response or increasing the understanding of the underlying PSP is basically at the root of this exploration versus exploitation dilemma. Let me take a minute to give my perspective on this. Suppose you're trying to find the optimal optimal X in terms of the highest value of Y. Basically, it should be somewhere around here. And you start with an experiment where you are using a design point here. You're basically choosing a material composition or the setup here. The dilemma is, where should I run my next experiment based on the model that I'm able to predict at this point in time? I could use the so-called exploitation, which is, I know the value of Y here, so let me try out the best Y in this particular region. That is, I'm trying to exploit the local curvatures around. Or I could just randomly explore at a particular point, or explore based on my understanding of where there is a large uncertainty in understanding the underlying relationship. Or we can use a combination of those where you can actually see how much of improvement or decrement you have with respect to the initial as well as the uncertainty. Combination of both the DC as well as AC information. So depending on how you design your search strategy, you can exploit or randomly explore, or you try to use this model to reduce the uncertainty, or you can use it to improve both the exploitation as well as exploration. The expected improvement, or EI, tries to strike a balance, but that may not be the only way to do this. There are quite a few methods that are designed for improving the knowledge as well as improving the response and achieve the balance between the two. So we can use, depending on the objective that we want. For example, if you want to understand the PSP relationship, you could possibly use more increased knowledge type acquisition function. And when you are trying to find a particular type of a material or a process recipe, you could possibly use one of these types of acquisition functions and so on. And once you use these acquisition functions, you can basically try to iterate and invert the model to be able to run the experimental iterations. And this type of forward and inverse mapping essentially constitutes the brain, and they get implemented into the modern AM bodies, essentially the hardware systems. When it comes to the hardware systems, they have evolved considerably from their initial stages. The initial ones have been mostly based on heuristics, and from the 2000 onwards, they became more and more automated systems with hard-coded logic. But in the last few years, they have evolved with a lot of autonomy built into them. That is the learning and adaptation. And if you look at some of these recent platforms laid out in this particular table, they have gone from purely automated systems to being endowed with a lot of autonomy. And from a forward modeling standpoint, they actually use some very interesting set of forward models, mostly surrogate models. And in terms of acquisition strategy, they use some of these acquisition functions that we laid out earlier. And these objectives range from biological systems, carbon nanotubes, all the way to hydrogen generation systems. But most of these, as you can see, are at the realm of what we call as benchtop chemistry type of systems. And the evolution, the jump to the manufacturing processes remains a very interesting challenge. In the remaining time, I will just play out one video of this existing system.
It communicates with a software control system wirelessly. It needs to be wireless because it's moving around a large space. The robot weighs out the solid catalyst, it dispenses the liquids, it shines the light onto the samples, it measures the outputs, which is hydrogen. And based on this output, the hydrogen emission from the experiment, it then makes a decision about what to do next.
Just like a human chemist, this robot needs to be able to adapt its workflow based on the outcome of its experiments. And this requires a computational solution.
If you work out the number of possible combinations of the components in the experiment, it's something like 98 million. So the robot uses an optimization algorithm using a method called Bayesian optimization to navigate that chemical space.
To help it work more like a human chemist.
So essentially, it's trying to use a Bayesian optimization framework to determine the right kind of experimental strategy. And it uses ECB as a way to, as an acquisition function in this particular case. And the last component of the body is not just about synthesis, but about the measurements. This becomes a very interesting challenge because if you look at the entire cycle of autonomous materials discovery and manufacturing, we have some advanced methods that we outline to learn and adapt. And there are some very sophisticated experimentation platforms as well as manufacturing platforms to create various kinds of materials and process chains. But the measurement systems to correctly assess the precise combinations and the structure remains the major bottleneck in this entire cycle. And there have been some interesting works in this area. One of the ideas is, can we actually club this characterization with processing? And can we do all of them in a single shot? And that, I think, is an interesting possibility. The smart hybrid platforms that we are working in provides one such opportunity here. And this hybrid platform essentially allows both 3D printing, machining, polishing, and also in situ measurement and possible characterization in a single platform. And since you're doing all of them with a single datum, it significantly reduces the process time. So you can actually use these experimental iterations more cleverly and more efficiently. And because of the sensors that we have incorporated, you possibly can achieve control beyond just the shape and morphology. Microstructure is still in works, but you can hope to achieve it much better compared to many other manufacturing platforms. And this machine has been endowed with 14 different sensors of different kinds. And the advantage to that is if you align the sensors well, you can possibly capture information from different multimodal aspects. For example, here you're looking at vibroacoustic data from the process, and you have the thermal, the heat, the temperature, and you also have the control data from the machine tool in itself. And you can actually have different kinds of cameras that are simultaneously gathering this information. And this information can be used to track the evolution of the process as it goes. And you can actually use it for mapping the trace of what the process was doing when a particular structure was realized. So you can actually make voxel to voxel comparison of the structure to property. In addition to that, this machine allows efficient processing of the materials. And as a result, using the same structure, you can not only get the material, but also create the samples, whereby you can actually get more consistent test results from characterization. So we could actually prepare the sample on the fly and create structures with the array of 10 nanometers if we need to, almost create metallic mirrors while you are 3D printing. And we can actually use the sensors to study the energy footprint and possibly optimize. And more importantly, one of the recent works that we have been doing is to use the images that was gathered ex situ to be able to quickly determine the hardness of the material using just the image measurements, and also using the sensor data from processing a hybrid cycle consisting of printing and machining. We could estimate hardness without having to take that sample and then go through the hardness testing routine. So there are quite a few interesting possibilities that emerge in this context. Given the time constraint, I would like to summarize this talk. I hope, based on the understanding of an AMDM system, as well as its brain body components, as well as the challenges, I hope we are getting some kind of a thought about the possible disruptive nature of this AMDM technologies. And as mentioned, it is a quite an interdisciplinary field. And for manufacturing as well as systems engineering community, the very fact of combining multiple processes to influence the structure, it's a tantalizing possibility. So you're not discovering a new manufacturing process in particular, but you are trying to discover a suitable manufacturing recipe. And the challenges in this is trying to grow, and it's taking the form of combinatorial manufacturing, multimodal manufacturing, and hybrid manufacturing, depending on which group you're looking at. However, in this context, there is one challenge, especially the systems engineering challenge, that has not been tackled much, which is here we assume that material precursors are available ready. We just completely ignore the supply chain whereby you generate those precursors. And I think there is some very interesting challenge, not just within the process chain, but the entire supply chain for this material. And also from a data science standpoint, it poses some very interesting opportunities from both learning and adaptation standpoint for data fusion, dimensionality reduction, and capturing this spatio-temporal evolution that I had mentioned. And also the works of Professor Ding and Professor Imtiaz Ahmed, they've been looking at recognizing and reacting for the surprises that are observed during these processes, because surprises often have been precursors to various discoveries that have happened over the history. So there are some very interesting data science and AI challenge for the industrial engineering community. And similarly, in the operations research standpoint, a lot of work in data-driven dynamic decision-making can be something that can become applicable to this particular AMDM platforms. A lot of works and advances in dynamic programming, reinforcement learning, federated learning paradigms that our OR community has been studying can be implemented here, and then those studies could be advanced based on some interesting nuances this platform presents. And similarly, the last, not the least, this collaborative robotics becomes extremely important here. That is how we can use the human intuition as well as experiences, as well as human skills to further advance the autonomous manufacturing remains an interesting possibility. And I hope this actually is something that our IE community also takes up as a possible avenue of application. So with that note, I would like to conclude this presentation, and thank you everyone for attending this talk.